Welcome everyone to the course Mechanics of Fiber Reinforced Polymer Composite Structures. Today we are going to discuss sample problems based on assignment number 1. I am a TA of this course. My name is Ananya Mandal. So let's start with some sample problems which will be helpful for you for solving your assignment 1 questions. So the question number 1 is, in composite materials the matrix phase is dash while the reinforced phase is dash. So options are option A continuous, discontinuous, option B discontinuous, comma continuous, option C heterogeneous, comma discontinuous, or option D stiffer, comma weaker. Now in a composite material there are mostly we talk about what is a composite. So composite has more than two constituents, and these different constituents either form the matrix or the reinforcement. As you can see in this diagram, so this is a reinforcement fiber and a polymer matrix. So mostly the matrix is the base and on which the reinforcement is attached. So matrix are also known as the polymer and the reinforcement here as this saying fiber. It can be of different forms, either flakes, particles, fibers, mats, etc. So that forms the reinforcement. Now, when we combine this reinforcement and the matrix, it forms the whole composite. As you can see here, this is the whole composite. Now, how to tell if which portion is continuous and which is not continuous? So, if we take one cross section of this composite, we can see we can differentiate the different reinforcement fibers, but these are not connected to each other. That's why we say that it is discontinuous. Whereas this matrix, when we move from one point or the other of this matrix, we can join them. So the matrix part is a continuous part. So the option for this question will be option A, that is the matrix phase is continuous while the reinforcement phase is discontinuous. Next question is question number 2. Composite materials have dash constituents. Options are option A only two different, option B only a single, option C two or more different, or option D only three different. Now the definition of composite says that it has two or more constituents. Now how? So there are some examples you can see here. The first one is a carbon fiber and epoxy pipe. So in this, the reinforcement is the carbon fiber whereas the epoxy is the matrix. So this contains two constituents. Whereas the concrete is a mixture of adhesive and aggregate giving a rubber strong material that is very widely used. So a concrete is also known as a composite, but it has, as you can see, you can like visibly differentiate different parts of this composite. So these are different colors and different stones and gravels. So they are more than two. The cement is the matrix and the reinforcements are not only a single type but they are different types. Next is the hybrid composite. So in this hybrid composite, it can have a single matrix and the reinforcements can be more than one. As here, the white ones are glass fiber and the black ones are the carbon fiber. So these have two different reinforcements. So from these examples, you can tell that a composite material has two or more different constituents. So option C is the correct one. Next question is the constituents in a composite combined on a dash. Option A, microscopic level. Option B, macroscopic level. Option C, atomic level. Or option D, nanoscale level. Now, whenever we talk about composite, containing two or more constituents, another thought always comes to our mind is about alloys. Alloys, as we have already studied from childhood, it contains two or more metals combined on it. But how alloys are different from the composite? So the composites are combined at a macroscopic level, whereas alloys at a microscopic level. How to define that? So when you see a composite, you can visibly differentiate different parts of that composite, which is the matrix, which is the reinforcement. Till like mostly you can see it from your naked eyes, or if not, it's till a extent you can tell it. That's why we say a macroscopic scale. But alloys, if you have an alloy ring, You can't tell which metal atoms or molecules are present there by just seeing at it. You have to go to the microscopic level to see the different metal components present in that alloy. That's why we say that alloys are mixed at a microscopic level, whereas composite at a macroscopic level. Now in the live session, someone talked about fillers and additives. So fillers and additives, they are mostly added to enhance the properties of one of the constituents in the composite. They don't act as one of the part of the composite, but as a supporting part. That's why whenever we are studying the mechanical strength, the mechanical properties of a composite, those components which we consider for studying, for calculating the total strength of a composite, we consider those as the parts of the constituents of the composite. Whereas, such as the fillers are mostly added with the matrix, and that improves the properties of the matrix. But still, it will call the part of that matrix and not a matrix plus a reinforcement. That's why when we talk about fillers and additives, they are not termed as the reinforcement, but they are just a part of one of the constituents of the composite which enhances their property. So the answer of this question, that the constituents in a composite combine on a, and the answer will be macroscopic level. Yes. In class, sir also taught about nano composite. So from that you might have this doubt that okay, nanoscale level also composites can combine. So the basic definition of composite says that there is a mixing and macroscopic level, but with the advancement of technology, we are moving towards more advanced composites, and from that we can get a nanoscale nano composites also. But in basic definition, we say that composite is mixed at a macroscopic level. The next question, question number 4 is reinforcements generally act as dash members, whereas the matrix acts as dash. Options are A, binding, comma weaker. Option B, load bearing, comma binder. Option C, continuous, comma discontinuous. And option D, binder, comma load bearing. So the reinforcements that are mostly used are carbon, Kevlar, or glass. This can be either in the form of fibers or mats or chalk strands, anything. Okay, they can be particles, flakes, and anything. So reinforcement, there are different forms of reinforcement. And matrix is mostly the polymer which binds all these reinforcements together. So in the picture, first came was the polymer. So we already had our initial materials like metal and ceramic and everything, and then came polymer. But the polymer doesn't have mechanical strength comparable to that of the traditional materials. That's why to enhance that came the composite, which combines some kind of reinforcement to that polymer and improves its mechanical strength. And you can see here in the table, for the fiber, which is the reinforcement, the properties like the modulus, the shear modulus, Poisson ratio. So the modulus you can see is so much higher. The carbon fiber, the Kevlar, glass fiber is like 131 gigapascal, 75.8 gigapascal. Whereas for the matrix, it is very less. The modulus for like epoxy is 4.6 gigapascal. So comparatively, you can see how much difference is there between the mechanical properties of the reinforcement and the matrix. From that, you can get the answer of this question. So answer will be option B. That is, the reinforcement generally acts as the load bearing member, whereas the matrix acts as the binder. Why load bearing? Because the reinforcement material have higher mechanical strength, and it has that higher mechanical strength can bear more force to it. But in the same case, matrix doesn't have enough mechanical strength to bear that much load. So what it does, it binds those reinforcements together to form the composite. And also there is another function of matrix, that is dissipation of the energy. So when some force acts on a reinforcement part, this matrix will dissipate that force to the surrounding reinforcements. So that is also a function of the matrix. But the general function we can say is acts as a binder. So option D will be the answer, that reinforcement acts as load bearing, whereas matrix acts as the binder. The next question is, reinforcement phase is dash and the matrix acts phase is this. The options are option A, more stiff and strong, comma less stiff and weaker. Option B, less stiff and weaker, more stiff and strong. Option C, continuous, comma discontinuous, or option D, discontinuous, comma continuous. So the reinforcement about discontinuous and continuous we already discussed in question number 1, that the reinforcement is the discontinuous one and the matrix is the continuous one. So from this we can say option D is the correct one. Next is about which is strong and which is weaker. So we already compared the mechanical strength of the fiber and matrix and saw that the fiber, which acts as the reinforcement, has higher mechanical strength and is the load bearing part, whereas matrix is the binding part because of having less mechanical strength. That's why option A is the correct one, because reinforcement phase is more stiff and strong, whereas the matrix phase is less stiff and weaker. Question number 6. The constituents in a composite combine in dash scale, whereas those in alloy combine in dash scale. Options are A, microscopic, macroscopic. Option B, macroscopic, microscopic. Option C, nano, micro. Option D, micro, nano. So as I already discussed before, the difference in composite and alloy. So as I said, the materials that are used in a composite, the different constituents of a composite can be easily differentiated by a naked eye most of the time. That's why we say that they are mixed at a microscopic level. Whereas the alloys, the metals that are combined, we can't differentiate it just by looking at it. That's why it is combined at a microscopic level. So the answer of this question will be option B. The composite combine at macroscopic and the alloy combines at microscopic level. Question number 7. It says that Young's modulus and density of graphite fiber are 230 gigapascal and 1800 kg per meter cube respectively. Young's modulus and density of steel are 206 gigapascal and 7800 kg per meter cube respectively. The ratio of the specific modulus of graphite fiber to that of the steel is. Now this question comes from the concept that why composite? So when a composite was formed, we said that the mechanical properties of the composite is comparable to metal. That's why composite as a future can replace the metals in many applications. But one of the advantages that composite comes with is lower weight. When you compare the same mechanical properties of an amount of composite and metal, you will see this, the mass of the mass is very much higher than that of a composite. That gives the advantage to composite for future uses. For example, so currently we are using CNG cylinders in a car, and that CNG cylinder is made of metal, so it will have its own weight. That is also adding up in the efficiency of that car. Later, that CNG cylinder will be replaced by a composite one. So, composite which has the comparable mechanical strength like the metal, so it can withstand the air pressure, the gas pressure, the CNG pressure inside. Also, the weight of that cylinder is less. So, that will increase the efficiency of that car. Because weight also acts as one of the component which causes the consumption of the fuel. So putting that in mind, we can see that the composite, what is the advantage of composite, and the most the best thing about composite is its lower weight. So from that concept comes this question, where they are comparing the specific modulus. Now specific modulus formula you can see here. It is Young's modulus divided by the mass density. So the Young's modulus of both the reinforcement fiber and the metal will be comparable. Like you can see, the graphite fiber, which is the reinforcement here, has the Young's modulus 230 gigapascal and that of steel is 206 gigapascal. But the density is so much different for both these cases. So when we will find the specific modulus of the graphite fiber, that will be 230 by 1800, and the steel, that is 206 by 7800, and we have to find the ratio of the specific modulus of graphite fiber to that of steel. So when we find the ratio of these two, the answer will come between 4.8 to 5. Now this question number 8, is like the concept is same as the previous question, but here in the previous question they were talking about Young's modulus, here they are talking about the ultimate tensile strength. So the ultimate tensile strength and density of UD graphite slash epoxy. UD graphite slash epoxy, here it is talking about the whole composite. So here they only talk about the reinforcement, that is the graphite fiber. Here they are talking about the whole composite, that is the unidirectional graphite fibers are the reinforcement and epoxy as the matrix. Are 1500 megapascal and 1600 kg per meter cube. The ultimate tensile strength and density of steel are 648 megapascal and 7800 kg per meter cube. The ratio of specific strength of graphite slash epoxy to the steel is. So the formula of specific strength is the ultimate tensile strength divided by the mass density. So we have to find the ratio of specific strength of graphite slash epoxy to that of steel. That will be the ratio of the ultimate strength by mass density of the graphite epoxy by that of steel, and from that we will get the value between 11 to 12. So next question is question number 9. The glass fibers have dash chemical resistance and dash conductivity compared to carbon fiber. So these statements are something that are known to us. There are no like reasoning hard fast reasoning and conditions about it, but these are some known facts when we are comparing different reinforcement constituents. So whenever we are trying to form a composite, the first thing we have to decide on is the reinforcement, because that is the load bearing component. So according to the application, how much mechanical strength and mechanical properties are required to us, we will choose what type of reinforcement to use. And the most common reinforcement are glass, carbon and aramid. Now, and according to our application, we have to choose that reinforcement, and then we have to see which type of matrix is compatible to that reinforcement by studying on that TDS and everything. And from that, we can get our the final product, the final composite according to our application. So the first question number 9 talks about chemical resistance and conductivity. So the glass fiber has higher chemical resistance and lower conductivity compared to carbon fiber, which is option B. Question number 10 says that glass fibers have dash specific modulus and dash specific strength compared to carbon fiber. So the glass fiber have both lower specific modulus and lower specific strength compared to carbon fiber. As you can already see in this table where we talked about different properties. So the carbon fiber properties are very much higher than that of glass fiber properties. Also, from these properties, according to our final application, we can also choose which type of fibers to be used. For example, if we are making a vessel, a cylinder, where we have to store a very high pressure gas. So according to the pressure of that gas, if it is very high, like around 700 bar, then we will use carbon fiber because it has a very high modulus and strength. But if the pressure is very low, then we can like around 2 bar or 10 bar. Then we can also build that cylinder with a glass fiber. So it depends on our application what type of reinforcement we have to use, and we have to keep in mind these properties like glass fibers have higher chemical resistance and lower conductivity and lower specific modulus and strength. And according to our application, we have to choose which reinforcement we have to use. Next, last question number 11, is that a lamina is dash and dash. Options are A, heterogeneous, anisotropic. Option B, homogeneous, anisotropic. Option C, homogeneous, isotropic, or option D, heterogeneous, isotropic. Now, a lamina is a combination of the matrix and reinforcement. So, one layer of reinforcement and one layer of matrix forms one lamina. And when we have many stalks of this lamina forms a laminate. These are some terminology that sir has already taught in the class. Now, a lamina contains both the reinforcement and matrix. So, it will have the properties of both of them. So, the first thing they talked about is heterogeneous or homogeneous. And heterogeneous means that the properties are location dependent. So, a lamina will have both reinforcements lying in some pattern and matrix around it. So, if you pinpoint any part in that whole composite whole lamina, it can either fall on a part where it has only matrix, or it can fall on one part which is both reinforcement and matrix. So that means that both these points will not have the same properties. The properties are not uniform throughout the location of that lamina. That's why the lamina will be heterogeneous. And the next point is anisotropic or isotropic. So anisotropic means that the properties are direction dependent. Now we have two constituents in our lamina, the reinforcement and the matrix. The matrix is an isotropic material. That means in every direction, as it is a continuous phase, it will have properties similar in all the directions. That is our matrix. But the reinforcement, the fibers that we are using, it will have modulus different in like transverse modulus and the longitudinal modulus will be different. That means in x direction, if you stretch that fiber in x axis, it will give different strength, and when you stress in y axis, it will give different properties. That means it is not uniform. The properties are not uniform in all direction for the reinforcement. That's why the reinforcement acts as an anisotropic. Now, when you combine this reinforcement with the matrix, the whole lamina will also act as anisotropic because in every direction the properties will be different. So, the option here will be option A, that the lamina is heterogeneous and anisotropic. So, these are some of the questions. If you have doubt, you can write it in the comment section, or we can also discuss in our next class. Next class I will be taking assignment number 2, problems of assignment number 2, and you can also discuss the doubts from assignment 2 or the classes, live session, or the class videos that are taught by sir. So let's meet at the next class. Thank you.